Pumps play a critical role in the movement of liquids throughout a process plant. As an operator, your responsibilities include operating pumps as efficiently as possible and monitoring them to make sure they work properly. Many factors influence the operation of pumps. For example, how well a pump moves liquid from one location to another depends on factors such as the mechanical condition of the pump and the properties of the liquid. Another factor that is often examined when looking at the operation of pumps is head. Head is basically a measurement of pressure. It's the pressure caused by the weight of a column of liquid as a result of its height. Head measurements are usually given in feet. For example, in an open tank like this one, if the liquid level is 25 feet high, then there is 25 feet of head at the base of the tank. However, the amount of head at this pipe is different. The pipe is 2 feet above the base of the tank, so the amount of head at the pipe is only 23 feet. The head caused by a non-moving liquid as a result of its height is called static head. The static head exerted on the inlet of a pump is measured from the center line of the inlet to the level of the liquid. In this case, there's 23 feet of static head at the inlet of the pump. The head at the inlet of a pump is often called the suction head. The head at the outlet of a pump is usually called the discharge head. Another way of looking at head is by relating it to pressure. For example, the amount of pressure at the discharge of a pump that's running can be viewed as the height of a column of liquid that the pump's discharge pressure will support. This imaginary column of liquid represents head. If the pressure can support a column of liquid 30 feet high, then the pressure is equivalent to 30 feet of head. The term head can be used to describe many conditions at the pump, regardless of whether or not the pump is operating. For example, let's say that in this system, the pump has been shut down. Under these conditions, the pressure exerted on the inlet and outlet of the pump are results of the height of the liquid above the pump's inlet and outlet. In other words, if head was measured at the discharge of the pump, it would be the same as the height of the liquid in the tank above the discharge. The amount of head or pressure at the pump's discharge and suction will change when the pump is started and the liquid begins to flow. At startup, the suction head will drop momentarily, then increase slightly as flow increases. However, its level is lower than when the pump is shut down. The discharge head produced when the pump is running is higher than when the pump is shut down. The head that exists when a liquid is in motion is sometimes called dynamic head. The amount of head or pressure produced inside the pump can be referred to as total head. Total head and the other types of head are characteristics that are taken into consideration when a process system is designed. Design engineers select pumps that will meet the requirements for each of the processes that are planned. When a pump is selected, it is chosen for a specific combination of head and flow. Head and flow are also examined to determine how well the pumps in a plant are performing. As an operator, your main concern in determining a pump's performance is whether or not the pump is supplying the correct pressure and flow. The values for proper pressure and flow are often based on the pump's design characteristics. One way of examining a pump's design characteristics is with pump curve graphs. This one shows the pump's head curve, which represents how much head or pressure the pump should produce for various flow rates. The horizontal axis of this graph is marked to represent flow rate. Flow rate can also be referred to as the pump's capacity. It can be marked in units such as gallons per minute, or as a percentage of pump capacity. For example, 100% is equal to the maximum volume of fluid that is moved by the pump under normal conditions. This is the pump's optimum operating capacity. However, many pumps can be operated at capacities greater than optimum. The vertical axis of this graph shows head in feet. The curve shows that the amount of pressure that this pump produces decreases as the flow increases. Since this curve represents what is expected of the pump, it can be compared with actual values for total head and flow to see if the pump is performing the way it should. Another type of curve, the power curve, shows how much electrical power a manufacturer expects will be used to operate a pump at given flow rates under normal conditions. We can see that this pump requires low power at a low flow rate. As the flow increases, the power needed also increases. We can use this graph to look at another pump characteristic, efficiency. The efficiency scale goes from 0% to 100%. A pump's efficiency varies depending on the percentage of its capacity that is being used. The efficiency curve begins at 0 on both the efficiency and capacity scales and rises to a maximum value near 100% capacity before falling off again. The point of maximum efficiency is the point where the pump provides the maximum flow for the least amount of power. If the other plant concerns, such as safety and production, allow it, this is the most desirable flow rate at which to operate this pump. Pump curves are often provided by manufacturers to help describe how pumps are supposed to perform. By comparing actual data from a pump with the information provided by the curves, a pump's performance can be determined. Much of the information contained in pump curves is the basis for data in plant procedures and information about pump performance that's passed on from one operator to another. The point is, there are many aspects to pump performance. The more you know about pumps, the better able you'll be to operate them safely and efficiently. As an operator working with many types of pumps, you'll need to be aware of conditions that can cause damage to pumps. One of these conditions is called cavitation. Cavitation is directly related to the amount of head or pressure at the suction of a pump. If the suction head drops below its designed value for the system, the liquid being pumped can flash to a vapor. This is when cavitation happens. Cavitation is the formation and subsequent collapse of vapor bubbles. Cavitation normally begins in the suction of a pump, where the pressure is the lowest and liquid is drawn into the pump. If the pressure of the liquid decreases too much, the liquid will vaporize or boil. When this happens, bubbles form and travel with the liquid in the pump. As thousands of these bubbles travel toward the higher pressure areas in the pump, they are compressed until they can no longer withstand the pressure and collapse or implode violently. As liquid rushes in to fill the collapsing bubbles, it strikes the inside surfaces of the pump and gradually wears away pump material. The result is a sandblasting effect on internal pump components, such as this impeller. This kind of damage decreases the performance of the pump. To prevent cavitation, the amount of suction head must be kept above a minimum value that has been determined for the pump. This value is known as the minimum net positive suction head. Minimum net positive suction head is the pressure just above where the liquid will boil for a given flow and temperature. If the suction head of a pump drops below the minimum net positive suction head, cavitation will occur. It's important to monitor suction pressure to ensure that it does not drop below the minimum net positive suction head for the pump. However, pressure is not the only factor that determines whether a pump cavitates or not. Since cavitation occurs when the liquid begins to vaporize or boil in the pump, the higher the temperature of a liquid, the more likely it will boil and cause cavitation at a given pressure and flow rate. The values for minimum net positive suction head for a pump are normally based on the type of liquid in the system and the temperature the liquid's expected to be at when it enters the pump. In most cases, the minimum net positive suction head is calculated for each pump. Then it's converted to units such as level or pressure. For example, pumps draw liquid from these tanks. Before a pump is started, an operator checks to make sure that the liquid in the tank that feeds the pump is above a minimum level to ensure that there will be enough suction head to prevent cavitation. In a different situation, operators monitor a pressure indicator to help maintain the inlet pressure for a pump. In this case, the value for minimum net positive suction head is converted to units of pressure. In this topic, we looked at some of the basic principles of pump performance. We covered the meanings of static head, dynamic head, suction head, discharge head, and total head. We also discussed a condition called cavitation and learned how it relates to suction head. Now is a good time to try some practice questions. The amount of head or pressure produced inside the pump can be referred to as total head. Total head and the other types of head are characteristics that are taken into consideration when a process system is designed. Design engineers select pumps that will meet the requirements for each of the processes that are planned. When a pump is selected, it is chosen for a specific combination of head and flow. Head and flow are also examined to determine how well the pumps in a plant are performing. As an operator, your main concern in determining a pump's performance is whether or not the pump is supplying the correct pressure and flow. The values for proper pressure and flow are often based on the pump's design characteristics. One way of examining a pump's design characteristics is with pump curve graphs. This one shows the pump's head curve, which represents how much head or pressure the pump should produce for various flow rates. The curve shows that the amount of pressure that this pump produces decreases as the flow increases. Since this curve represents what is expected of the pump, it can be compared with actual values for total head and flow to see if the pump is performing the way it should. To prevent cavitation, the amount of suction head must be kept above a minimum value that has been determined for the pump. This value is known as the minimum net positive suction head. Minimum net positive suction head is the pressure just above where the liquid will boil for a given flow and temperature. If the suction head of a pump drops below the minimum net positive suction head, cavitation will occur. As an operator, you're responsible for monitoring pumps in your facility. This involves making routine checks to make sure that they're operating normally and efficiently. Making these routine checks is a good way to help avoid costly and unnecessary shutdowns. With experience, you'll be able to tell right away when a pump is not working properly. Before you go out to inspect any pump, you should know how the pump normally operates. That includes knowing the pump's normal flow rates, operating temperature, and its normal suction and discharge pressures. You should also learn about any special features the pump has and what type of liquid it pumps. In addition, it's a good idea to become familiar with the pump's operating history. It will help you identify any recurring problems with the pump and may make troubleshooting a problem easier. Pumps can experience a variety of problems, and each problem can have a variety of symptoms. In spite of that, there are some general types of operating checks that can be made on all pumps. These basic operating checks relate to 3 of your senses. The checks involve looking, listening, and feeling for symptoms of pump problems. Looking for symptoms of problems often starts with instrumentation for the pump. As an operator, your main concern in determining a pump's performance is whether or not the pump is supplying the correct pressure and flow. Improper pressure or flow readings could be caused by a variety of problems. Some deal with the process fluid, and others are more mechanical in nature. Take some time now to learn more about the causes of improper pressure or flow. An abnormal change in pressure or flow can occur relatively suddenly, or it can be very gradual. If instrumentation shows a slow, gradual decrease in flow or pressure, it could be a sign that the pump's internal parts have worn, or that a condition is getting worse. So it's important to be alert to even subtle changes in instrumentation readings that may indicate a problem. In addition to looking at instrumentation, the pump itself should be checked for symptoms of problems. For example, operators should check for overheating by feeling the pump and motor casings and the bearings to get an indication of their temperatures. However, this must be done carefully because overheated components could cause burns. When more precise temperature readings are required, it's usually necessary to use a temperature instrument, such as a pyrometer, to monitor equipment temperatures. In addition, some pumps have indicators for bearing and lube oil temperatures. An increase in temperature could mean there's a problem with the lube oil supply, which is causing the bearing to overheat. This pump is running normally. The operator knows from experience that the pump sounds the way it should. Symptoms that indicate problems include excessive noise or unusual sounds. Some problems have their own distinctive sound. For example, a loud rattling or clanging sound could be caused by a broken pump part or a foreign object loose inside the casing. A howling or growling sound usually indicates worn or damaged bearings. It usually means that there's a lubrication problem. A high-pitched screeching is commonly produced by metal-to-metal contact between rotating and stationary parts. It could also indicate a lubrication problem or improper alignment or clearances between parts. While some problems have distinctive sounds, others simply produce excessive noise or vibration. Checking for unusual vibration is a common part of a pump inspection. A quick check can usually be accomplished by carefully touching the motor and the pump with a bare hand. For a more detailed examination of vibration, vibration detection instruments can be used. These instruments are extremely sensitive and collect various types of data on the nature of the vibration. After the data is collected, it can be analyzed to determine if problems exist in a pump or its driver. So far, we've been discussing some general symptoms of abnormal pump operation. Although we looked at each one separately, many symptoms are related. When you detect one symptom, be sure to look for others that could help narrow down the cause of the problem. Let's pause here to give you a chance to check your understanding of symptoms of pump problems. Checking for leaks is a routine part of inspecting pumps and their related equipment. Here, the operator begins with the suction piping, checking the suction valve packing and gasket for process liquid leaks. Then he turns his attention to the pump itself. Pumps that use packing often need a small amount of leak-off to cool and lubricate the packing. A trickle of liquid is normal. Unlike packing, mechanical seals should not have a noticeable leak-off. If liquid is leaking from a mechanical seal, the seal has failed and action should be taken to have the pump repaired. After checking packing or seals, the operator looks over the rest of the pump. Here, he checks the bearings to see if there are any oil leaks. Finally, he looks over the pump's discharge piping for the same things as with the suction piping. If he finds a leak, he'll trace it to its source and then report it to his supervisor. When you hear a rattling noise that sounds like marbles rattling around inside the pump, it's usually a sign of cavitation. Other signs of cavitation include fluctuations in discharge pressure and sometimes an overheated pump casing. Cavitation can also cause a decrease in flow. The extent to which flow decreases depends on how bad the cavitation is. Cavitation is usually violent, and if it's not corrected, the pump can be damaged. To stop or minimize cavitation, the suction head must be raised above the minimum net positive suction head for the pump. Sometimes this can be done by cutting back the flow on the discharge side of the pump. Restricting the flow of the fluid as it leaves the pump basically increases the pressure in the pump. Increasing the pressure will help keep the fluid from boiling and causing cavitation damage. However, restricting discharge flow could affect processes in the plant. So it's normally done temporarily if plant procedures allow it until other actions can be taken to stop the cavitation. In some cases, cavitation can occur because the temperature of the process fluid is too high. This causes the fluid to boil when it experiences the drop in pressure as it enters the pump. In this case, the temperature must be lowered to eliminate the cavitation. In this topic, we saw how important routine inspections can be in locating problems that could cause damage to the pumps in your facility. Experience with your facility's equipment and knowledge of the basic operating conditions for each pump will help you to recognize when something's wrong with the pump. It's then your job to report problems to your supervisor. Take a moment now and try some practice questions. Unlike packing, mechanical seals should not have a noticeable leak-off. If liquid is leaking from a mechanical seal, the seal has failed and action should be taken to have the pump repaired. Cavitation is usually violent, and if it's not corrected, the pump can be damaged. To stop or minimize cavitation, the suction head must be raised above the minimum net positive suction head for the pump. Sometimes this can be done by cutting back the flow on the discharge side of the pump. Restricting the flow of the fluid as it leaves the pump basically increases the pressure in the pump. Increasing the pressure will help keep the fluid from boiling and causing cavitation damage. However, restricting discharge flow could affect processes in the plant. So it's normally done temporarily if plant procedures allow it until other actions can be taken to stop the cavitation. In some cases, cavitation can occur because the temperature of the process fluid is too high. This causes the fluid to boil when it experiences the drop in pressure as it enters the pump. In this case, the temperature must be lowered to eliminate the cavitation.